Hello, Algebra 2 students. Today we're going to look at more polynomials that we're going to factor completely. So our goal is to turn the sum or difference, it looks like this guy is just a pure sum of different terms, into a product, and we're also going to list all the zeros for that polynomial. So of course there's a few different strategies you can pursue. The one we're going to mainly investigate in this video is using synthetic division in our calculator. So let's go ahead and stick this in our calculator to begin. So I'm going to go to my calculator and stick it in y equals. So I have nothing there. If you have any plots on, of course, turn those off. Mine are all off because none of them are bold up there. Okay, so I'm going to put my polynomial in. I'm going to go zoom standard just to start out and see if I can find a starting zero to begin my synthetic division. It looks like I have two zeros that I can play with here. I could of course go ahead and calculate those zeros, but it looks like that one's -1 and that one's -2. Since I've got to use synthetic division to test them, I might as well just test them out. So coming over here, I'll use synthetic division. Let me go a little bit more this way. Okay, so the first zero we wanted to test was, looks like -1 might work. So I'll do that, and I'll peel off my coefficients so I can use them for my division. Okay, bring this one down. Of course, multiply these. We're going to be adding as we go. So add 7 and -1, multiply, add. Multiply, add. Oops. Multiply and add. So you can see that I have now some evidence that -1 is a zero because when I synthetically divided it, my remainder is nothing. I was already expecting that from the graph. I'm also expecting from the graph to see a 0 at -2. Let's see if that is in fact true. So let's come in here and do that synthetic division. I think I'll just go ahead and use purple this time. So here's my purple. Get another synthetic division line going. And I'm going to be testing -2 this time. Bring down the 1, multiply, and add. Multiply, and add. Multiply, and add. I was expecting that as well because my graph already told me it was a 0, so I was expecting to get a remainder when I divided by -2. So, why would I go ahead and do this process? Remember, the reason is because we need this quotient. We need this quotient because a polynomial that is 4th degree, like this quartic pentanomial right here, it's 4th degree, fundamental theorem of algebra says it has 4 complex zeros. Our graph is showing us 2 real zeros. There, of course, might be another real zero or 2 more real zeros. I can't see those right now. I could, of course, zoom out on my graph. It's possible that, in fact, it eventually comes back over and goes like this, or something like that outside my window. But since I've got a parabola that's left, I know this is a parabola because if I start with 4th degree and divide once, I get 3rd degree. If I divide again, I get 2nd degree. So I know a whole lot about parabolas by now. So you know what? Since I don't see them, I'm going to assume that these final 2 answers are probably imaginary, and just work with that parabola. So I'm going to turn off my computer now, get that weird hypothetical drawing out of the way, and work with this guy. So what I have here is x squared plus 4x plus 12. I could work with this any way I know to work with parabolas, completing the square, factoring, quadratic formula. If I try to factor it, 4 and 3 don't make 4. 6 and 1 don't make 4, and of course 12 and 1 don't make 4. I don't think there's any way to factor this. We're going to have to use our quadratic formula. So let's go ahead and do that. So we'll say x equals -b plus or minus square root b squared minus 4 times a times c all over 2 times a. And I'll simplify. So that's going to be x equals -4 plus or minus 16 minus 4 times 12 is 48 over 2. So I'm going to keep simplifying over here. So that's x equals, I'm going to just do this already. This division is -2 plus or minus the square root. 16 minus 48 is -32 over 2. So that's going to be x equals -2 plus or minus the square root of 16 times 2I, because the square root of a negative is of course imaginary. So that's going to be -2 plus or minus 4 root 2 over 2I, which is -2 plus or minus 2 roots of 2I. So I think I've done all my work now. I need to assemble my final answer. I'm going to definitely be expecting you to assemble these this way. So let me erase some of my division, get it out of the way. We'll remember what was there though. So completely factored h of x looks like, those two factors I kind of erased them, but I think we said -1 was a 0, right? So the factor that goes with -1 is the quantity x plus 1. The second one, which I also erased, it was right here a second ago, should be in your notes, is -2. So the factor that goes with that is the quantity x plus 2. So the other factor that I have left is this irreducible, that's what you call it. If it results in complex number answers, you know that it's irreducible. It can't be factored or reduced further. So you're going to write that as the final factor. So that is the final completely factored version of this quartic pentanomial. The other thing I wanted you to do, whether or not the book's directions say so, is to list the zeros. We've of course already got those, we just need to assemble them. So the zero that makes this factor 0, and hence everything 0, is -1. This is the corresponding factor right here. The corresponding thing that makes this factor 0 is -2. And we just spent all this time with our beautiful quadratic formula to find those other two zeros. So we've got -2 plus 2 roots of 2I and its conjugate, -2 minus 2 roots of 2I. 1, 2, 3, 4 zeros for a 4th degree. That satisfies the fundamental theorem of algebra. Let's look at one more in this tape before we go forward. So one more polynomial function. I thought this one we might investigate would have a little bit more variety. So I cooked one up that was 6th degree. So let's look at f of x equals x to the 6th power minus 8x to the 5th power, and so forth. So this time I want to go to my calculator to begin as well. So I'm going to do that. Okay, here's what the graph looks like. Still working. So you can see it did something there and then it did something here. It's a little mysterious what's going on. Since it's 6th power, I should expect the end behavior to look like this. I think I'll make the window go up a little bit more, maybe like 100. See if that clarifies the issue. So now we can see that it looks like it comes down and touches the origin and then maybe at 4. So I'm going to try the origin to begin my synthetic division. So I'm going to go and say 0, 1, -8, and so forth. Notice I am missing the x and the constant, so I need to hold those with place values of 0. Okay, so here we go, synthetic division time. Bring down the 1, multiply, add, multiply, add. Well, multiply, now add these, multiply those, add these, multiply those, add these, multiply those, add these, and this last part's going to be pretty boring. So it's clear that that is in fact a 0, just like our graph was telling us. What's special about this problem is that you also have not just it going through at this point, but it bounces. That is called multiplicity. This 0 happens more than one time. In your notes, you should record that a bounce means that the 0 is repeated. So I'm going to use 0 again. So here we go. So we've also got a bounce at 4, so we're going to actually test that 0 twice as well. So we'll synthetically divide it once. Multiply, add, multiply, add, multiply, and add, multiply, and I need your calculator on that one, but I think it's 144. And add those up, and you get 0. So I knew that would happen because I see the 0 on the graph. Since it bounces, I'm pretty sure 4 is going to work again as well. So I'm going to go ahead and do that one as well. Bless you. Multiply, add, multiply, add, multiply, and add. There's confirmation that it worked a second time. So now you might be asking yourself, why did I do all of that? Well, we know that there's going to be 6 zeros. We can only see 1, 2, 3, 4 of them. Maybe the other ones are lurking outside of our window, but I don't think that's what's happening here. So we started with the 6th power. This is 5th power, 4th power, 3rd power. Down here we have a parabola, and I think it's a pretty simple one. The parabola, in fact, is x squared plus 9, if you look at that guy. So that's an easy one. We don't even have to apply the quadratic formula. I'm just going to move the 9 and solve. So my final 2 zeros are imaginary, because the square root of negative 9 is imaginary. So there we go. I'm going to compose my answer, or assemble it now, show the factorization. So we had 0 twice. That means each one of those is going to be x squared times. We factored. Of course, that's turning a sum or difference into a product. We've also got 4, so that factor is going to be negative 4, x minus 4, the quantity. We've got that again, so I could write another x minus 4, or I could just say I have 2 of these quantities, quantity squared. The other final factor didn't work out to be a line. It was just a quadratic. So I'm going to say x squared plus 9. And then, of course, just like on the other ones, we want to write down our zeros. So I'm going to say my zeros are, we've got them all right there, 0, 0, 4, 4, 3i, and negative 3i. 6 zeros for a 6th degree. Let's do one final example. Let's try to do it without our calculator in order to think about the graphs of these polynomials a little more as we move towards next week. So I'm going to take my graph away and do one more problem. We'll call this one k of x. So k of x is going to be negative 54 x to the 5th plus 16 x squared. So this one I'm going to do my best to not use my calculator on. And I'll build the graph from just what I do with it. So if you think back to your factoring tools, the basic ones, standard trinomial, difference of squares, and what they share. This guy shares something. What do they share? Well, you might have to play with your calculator, but I don't think we need to. They share 2 at least, and they definitely also share x squared. So I'm going to pull out a negative 2x squared. You could just as easily pull out a positive 2x squared. What's left? 54 over 2 is 27, and I pulled the negative out. Still got x cubed left, or 3 x's multiplied together. If I pull 2 out of 16, I have 8. I pulled the x squared out. But when I pull a negative out of a positive, I'm left with a negative. So there's that one. No synthetic division required so far. Hopefully this guy, at least if you've been taking advantage of some of the more sophisticated practice, just jumps out at you. Hopefully this guy makes you think difference of cubes, because I see some really cubic numbers here. 8 is 2 cubed, 27 is 3 cubed, and x is of course x cubed. This is a classic example where you can use the difference of cubes. So I'm going to do that. I guess I could write down my difference of cubes formula. Hopefully we've seen that enough times to where we start to absorb it. It is something you need to memorize. So the difference of cubes is this. X and x squared make x cubed. A and a squared at the end make a cubed. If it starts minus, you start minus. You have to remember there's another thing in the middle, so that requires a bit of practice. And you also remember that there's always one minus. So if we've used it already, then these are both plus. So I'm going to use that to factor this. In this case, x isn't just x. X is 3x. So I'm going to go 3x here. 3x quantity squared is 9x squared. And I also need a 3x in the middle. My a is an a. In this case, 2 cubed is 8. So a is 2. So I'm going to put a 2 here. I need a 2 in the middle. And I need a 2 squared at the end. Minus means minus, so plus plus. I'm going to simplify that just one more time. But I think that's about all I can do with this guy. This is completely factored, k of x. There's what I'm searching for. If you'd have done this one with the synthetic division approach, you'd have gotten the same answer. Would have taken a lot longer. So, I also, once I've factored this guy like this, I don't really need my calculator. I can just draw the graph. I know what the zeros are. Let's write them down. The zeros are going to be 0 for this one, and it happens twice. So I'm going to actually have 0 twice. In other words, it's going to bounce on the graph. This one I might need to solve. We'll do a little scratch work over here. So I'll get 2/3. And this one, see how all those are positive a, b, and c's? I'm just guessing that I'm going to have imaginary zeros for this one. I'll confirm that with the quadratic formula really quick. So let me go through that really fast. Negative b plus or minus the square root of b squared minus 4 times a times c over 2a. So that's going to be 16 times 9. Oh, I don't want to do 16 times 9. 16 times 10 is 160 minus... I don't want to do it. $144. Oh, that's close. $36 minus 144. Going to go to my calculator for that too. It's negative 108. So this quadratic formula didn't work out so nice. 108 I can reduce. I'm going to try some big numbers first, like 36. Oh, I got lucky. Negative 6 plus or minus 36 times 3i over 18. So that's going to be negative 6 plus or minus 6 root 3i over 18, which is going to be negative 1/3 plus or minus 1/3 square root of 3i. But the whole point, after simplifying that down, is that these were imaginary. I suspected that from the beginning because all of these guys were positive, so I was picturing a parabola above the axis. Let's put all this information together. So I have all my zeros, just like we've been focusing on this assignment. 1/3 plus 1/3 root 3i, 1/3 minus 1/3 root 3i. Crazy how many 3's are in this one. Got all my zeros. I don't need my calculator anymore. I can put this together, and that's where we're heading next. I can put the graph together without it. Negative 54x to the 5th. Any odd function should look like this. If it's negative, that flips it. So I know my behavior is going to look like this and like this. In other words, the flip of that guy. I also know what my zeros are. I know that one of my zeros is 0, and the second one means it bounces there. I know that my other 0 is 2/3. So if this is 1, my function's going to do this. It's going to go down. It's going to hit 0. Since it happens twice, it's going to bounce. I don't know exactly how high it's going to go, but I know definitely it's going to come back and pass through at 2/3. So it's going to bounce, probably not too high, come back right there at 2/3. And there's no other zeros. There's no other zeros that are real. They're only imaginary. So I know this is going to come and connect with this down like this now. That's a basic picture of my polynomial. I don't need my calculator for it anymore or anything like that. That's what it's going to look like. This is k of x. So that's what we'll focus on last in this unit, is learning to picture a graph without ever touching our calculator. I'll see you next time.